Welcome to Chapter 3, Chemical Foundations, Elements, Atoms, and Ions. In this chapter, we will move from the general idea of matter to the particles and patterns that explain the composition. We will begin with the elements, including their relative abundances, names, and symbols. We will then examine Dalton's atomic theory and learn how chemical formulas represent compounds. Next, we will look inside the atom and discuss electrons, protons, neutrons, then isotopes, atomic numbers, and mass number. We will also use the periodic table to organize the elements and compare metals, nonmetals, and metalloids. Finally, we will study how atoms form ions and how those ions combine to make electrically neutral compounds. That'll be a very, very important step. Section 3.1 introduces the elements. There's a lot of them. We'll have three objectives. First, we will learn about the relative abundance of the elements. Abundance means how much. The elements are not present in equal amounts. The most common elements depend on which part of the world or what type of material we are examining. The second, we will learn the names of some important elements. Third, we will use their chemical symbols. That's the fun one. The symbols form the basic language used in chemical formulas and equations, so accurate capitalization is extremely important. By the end of this section, you should be able to connect an element's name with its symbol, at least generally. I'm not asking you to memorize them, and explain why most abundant elements in the human body differ from Earth's crust, the ocean, and the atmosphere. The elements. All of the materials in the universe can be chemically broken down into about 118 different elements. Although the number of possible materials seem to be almost unlimited, those materials are built from a relatively small collection of basic substances. The diagram here compares the elements to the letters in the alphabet. Just like letters can be arranged in different ways to form many different words, atoms can be used to combine different arrangements and proportions to form different compounds. For example, the same small set of element symbols can be rearranged to represent different substances. The main idea is that the elements serve as the basic chemical building blocks of matter, while compounds are produced when atoms of different elements are joined together. I can spell lots of different words. Four of them. The abundance of elements in Earth. Believe it or not, the elements are not distributed evenly in our crust, oceans, and atmosphere. 9 elements account for about 98% of the total mass represented in the table we have here. Oxygen, the most abundant, at about 49%, followed by silicon, about 25%. Aluminum, iron, calcium, sodium, potassium, magnesium, and hydrogen make up the rest. The elements on the right side of the table occur at much smaller percentages. This helps explain why materials containing oxygen and silicon are common in the rocks and minerals. When we discuss abundance, remember that the table shows mass percent. It tells us what fraction of total mass is contributed by each element, not simply the number of atoms present. And we'll talk about that much later in the year, but it's important to know we're talking about mass percent. Abundances again. The elements found in living matter are present in very different proportions than what we find in Earth. I don't know if you guys know this, but you really don't have much silicon. In the human body, oxygen, carbon, and hydrogen, followed by nitrogen, are the most abundant elements. According to our table up here, oxygen accounts for about 65%, while carbon is about 18%, hydrogen 10, nitrogen 3. Calcium and phosphorus are also extremely important, and then we have magnesium, potassium, sulfur, and sodium. The comparison between this table and the one we were just looking at shows us why the abundance must be connected to what specific thing we're talking about. It's not the same on Earth's crust as it is in the human body. Carbon, however, is the central atom or element that is uh, just the most important to living matter, and its portion in the crust is very small. Ooh, here's a fun one. The word element can be used in several related ways. In microscopic form, an element may mean a single atom of that element. That first picture right there represents an individual atom. The macroscopic form, an element may mean a sample large enough to see and weigh. such as a piece of copper shown on the balance. That visible sample right there still contains an enormous number of copper atoms. The word can also be used in like a generic sense when we say the human body contains sodium or lithium. We don't mean free elemental sodium or lithium, that they're actually part of some uh, compound or in their ionic form. Context, when we're reading about the word, tells us the meaning being used. Names and symbols for the elements. Each element has a name and a chemical symbol. A symbol usually contains one or two letters from the element's name. The first letter is always capitalized, and the second letter, if it has one, is lowercase. Oxygen is represented by capital O, while krypton is represented by the capital K and a lowercase r. Some symbols do not closely match their modern English names because they come from Latin or Greek. Gold, for example, is AU from aurum, and lead uses PB from plumbum. Yes, it is. Those symbols are written exactly. The changing of the capitalization can change the meaning. For example, a one letter symbol and a two letter symbol are not interchangeable. Learning the common names of the symbols will help us relate formulas to periodic table entries. Section 3.2 focuses on atoms and compounds. First, we are going to learn about the major statements in Dalton's atomic theory. Dalton's model is an important starting point for explaining elements, compounds, and chemical reactions. We'll come back to that many times throughout the year. Second, we will understand and illustrate the law of constant composition. This law states that particular compounds always contain its elements in the same proportion by mass. And yes, that's a lot. We'll get to it. And third, we're going to learn how the chemical formula describes the composition of a compound. A formula identifies the elements present and uses subscripts, little numbers, to show the relative number of atoms on each element. All of those ideas put together connect the microscopic particles in a substance with the symbols and numeric relationships that we will use to describe in a substance. Law of constant composition. Looks really easy right there, very short. Um, we'll get to it. The law of constant composition states that a given compound always contains the same proportion by mass of the elements of which it's composed. In normal words, a pure compound has a fixed composition. Composition meaning how it is made up. Water is always made from hydrogen and oxygen, and it always has two hydrogen and one oxygen, as you've probably heard H2O. That mass relationship, how much oxygen weighs and how much hydrogen weighs, is always the same, regardless of if the water is in a lake or if it's in a laboratory or a sealed bottle or on the moon. If it's water, it's two hydrogens and one oxygen. If the proportions were different, let's say two oxygens and two hydrogens, then we have hydrogen peroxide. And I don't know about you guys, I don't want to drink that. This law supports the idea that compounds contain atoms in fixed combinations. It also provides a way to distinguish a compound from a mixture. Mixtures have variable composition just by the nature of what a mixture is. It is not the same thing throughout, but the pure compound contains the same elemental composition from any sample from anywhere in the universe. Dalton's atomic theory. All right, so there are five major ideas for Dalton's atomic theory, and you do need to know all five of them. So let's go in order. First, all elements are composed of atoms. If you didn't know that one, go back about four slides or the beginning of the first lecture video and watch it again. Second, Dalton proposed that atoms of a given element are identical. Third, atoms of different elements are different from one another. Fourth, compounds consist of atoms of different elements combined together. And finally, atoms are not created or destroyed during an ordinary chemical reaction. Instead, the atoms are rearranged into new combinations. Some parts of Dalton's original theory have been modified as we have learned more about the atomic structure, but the base theory established an important particle level explanation for chemical composition and reactions. The central idea that chemical reactions rearrange atoms rather than creating or eliminating them. That will be especially important when we begin balancing equations. I promise. Concept check. Which of the following statements regarding Dalton's atomic theory are still believed to be true? 1. Elements are made from tiny particles called atoms. 2. All atoms of a given element are identical. 3. A given compound always has the same relative number and type of atoms. And 4. Atoms are indestructible. I'll give you a second to think. All right. It's been long enough, probably because Wayground already made you answer the question. We found out that number 2 and number 4 are not correct. Why are they not correct? 2 states that all atoms of a given element are identical. We're going to learn about a fun thing called isotopes. Isotopes are the same element because they'll have the same number of protons as all other elements of that kind, but they will have a different number of neutrons. So that cannot be true. We'll also learn about ions, which will have the same protons and neutrons, but will have a different number of electrons. Those will also not be the exact same as their non-charged counterparts. So we know both of those can't coexist. And if you've done your vocab already, you already knew that. And then the last one we'll talk about at the very end of the year, but that is nuclear chemistry. That is how some nuclear reactions take place, is by the separating of the components of an atom. Good job. Formulas of compounds. Oh no. A compound is represented by a chemical formula. The formula, right there, shows both the kind of atoms present and the number of each by the subscript. The example that we have right here is glucose, which is the simple sugar. It is the formula C6H12O6, where we have 6 carbons, 12 hydrogens, and 6 oxygens. Subscripts show that one molecule of glucose contains all of those together in that proportion, a 6 to 12 to 6 ratio. A chemical formula does not simply list ingredients, and we'll learn later that it actually describes the composition. But for now, we're just going to be going off of the number. All right, so when we write formulas, there are 3 rules that we need to know. The first, each type of atom present is represented by its elemental symbol. Second, the number of atoms in each type is shown by a subscript written in the lower right of that elemental symbol. And third, when only one atom of a particular element is present, we do not put a 1 subscript. For example, in H2O, the 2 applies only to the hydrogen, and oxygen does not get a 1 subscript because it only has 1. You'll learn throughout your chemistry class that chemists get very lazy because there's a lot to write. So if there's a 1, it's implied, we just don't write it. But you should also know that we can't just randomly change those numbers. They're not out in front. They're always to the right and small, because the difference between H2O and H2O2, again, is water and hydrogen peroxide. Those are not the same thing. We don't want to pretend they're the same thing. Section 3.3 examines the atomic structure. We will first learn about the internal parts of the atom, and then we'll learn about Rutherford's experiment and explain how its results changed the accepted model of the atom. Next, we will describe the important features of the 3 major subatomic particles, the proton, neutron, and electron, and then we'll define isotopes, atomic numbers, and mass number. And then finally, we will learn to use isotope notation, which places the mass number and the atomic number beside an elemental symbol to describe that particular atom. This section moves away from the early experimental evidence of the modern picture of small central nucleus surrounded by electrons. The structure of the atom. Experiments by J.J. Thomson show that the atom contains negatively charged particles called electrons. You will need to know that J.J. Atom did this, so make sure you know that he did this experiment of the cathode ray tube. The diagram shows the cathode ray tube. A beam travels through the evacuated glass tube from one metal plate to the other. When electrically charged plates are placed near the beam bends towards the positive plate and away from the negative plate. This behavior showed that the particles in the beam carried a negative charge because the same type of behavior is seen regardless of the metal used in the apparatus. Thomson concluded that electrons were present in all atoms. He was right. It was important because it demonstrated that atoms are not indivisible solid particles. Instead, the atom had an internal structure somehow that included smaller charged particles. And he only knew that something had to be negative. Because remember, from magnets, like charges repel each other. That's also a huge part of chemistry much later on, but you do need to remember your magnets. Oh, the plum pudding model. After discovery of the electron, scientists needed a model that included both negative electrons and the overall neutral charge of an atom. The plum pudding model pictured the atom as a diffused sphere of positive charge with a bunch of negatively charged electrons scattered throughout it. Uh, I don't have a good picture of plum pudding, but imagine you've got a nice cookie and there's a bunch of raisins in it. That's it. In the diagram, the blue sphere represents the spread out positive charge, and the red particles are supposed to be the electrons, which would be the negative charge. The positive and negative charges would balance, making the atom neutral overall. This model fit some of the evidence at the time, but it had not yet been tested against the distribution of positive charges and the mass inside the atom. Rutherford's experiment, that we'll look at on the next one, provided evidence that positive charge was not spread evenly throughout the entire atom. I hope you're ready. The suspense is killing me. The Rutherford experiment is a lot to take in, and we will watch a video of this in class, but generally, it directed a beam of positively charged, what we call alpha particles, towards a piece of metal foil. A screen, like a big, like aluminum foil screen, detected where the particles traveled either past or through it. Most of the alpha particles passed straight through the foil. Some were deflected at small angles, and a very small number were scattered sharply. The apparatus is important because the path of a charged particle can reveal how charge and mass are distributed inside the atom. If the positive charge were spread out as proposed by that plum pudding model, the particles should have experienced only small, gradual deflections, and they shouldn't have seen any of those sharp deflections. The unexpected large angle scattering requires a different model. More or less, Rutherford's experiment, right? They said if it was always an even distribution of positive and negative charge, you should see the same thing every time you shot the alpha particles through this piece of metal. But since they didn't see that, they knew that there had to be some unevenness inside of an atom, which they're about to find out. Spoilers. More about that experiment. This will help explain question mark. This diagram is going to compare the predicted results, which are the ones on A, versus what they actually saw, which is on B. On left, the plum pudding model predicted that the alpha particles should pass through the atom with only small changes in direction because the positive charge is spread through the entire volume. On the right, the actual results show that most of the particles pass straight through, but a few were strongly deflected. Rutherford concluded that most of an atom is empty space. The atom's positive charge is the most of its mass, so it must be concentrated in a very small, dense area. A particle passing through the empty space could continue forward, while one passing close to that concentrated positive region would be pushed sharply away. So Rutherford began to develop this model, which is the atom has a very small nucleus, is what he called it, that was positively charged. He used the new word protons, and that's what we're going to continue to use, and uncharged neutrons. The electrons occupy the space around the nucleus, and the diagram emphasizes the tremendous difference between the size of the nucleus and the overall size of the atom. The nucleus is relatively small compared to the region occupied by the electrons, yet it contained nearly all of the atom's mass. This meant that most of the volume of an atom is relatively empty space. The positive charge is concentrated in the nucleus, while the negative electrons are found outside of it. This arrangement right here explains why most alpha particles passed through the foil, while others were strongly deflected. All right, this table compares the relative mass and charges of the electrons, protons, and neutrons. On the relative mass scale shown, the electron is assigned a mass of 1 for comparison. A proton has a relative mass of about 1836, and a neutron has about a relative mass of 1839. So yes, the neutron has a little bit more. This shows that protons and neutrons are way bigger than electrons and almost equal masses. For what we talk about, protons and neutrons will be equal, uh, unless I ask, is a neutron bigger than a proton? And you'll say yes. An electron has a negative charge, a minus one charge, and a proton has a positive one charge. But a neutron, neutral, has no charge. So protons and neutrons are located in the nucleus, while the electrons occupy the region outside. In a neutral atom, the number of protons and electrons needs to equal 0. So if I have, let's say I'm oxygen, I have 8 protons, I have 8 electrons. We don't care necessarily about the neutrons because they don't change anything for the relative charge. Now, if I have 8 neutrons, I am normal oxygen, but if I have 9, then I am an isotope, which we'll talk about soon. Oh no, soon is now. Isotopes are atoms that have the same number of protons, but a different number of neutrons. The two diagrams represent isotopes of the same element, it's sodium. Because both nuclei contain the same number of protons, both have the same atomic number, and belong to the same element, sodium. Their neutron numbers differ, so the mass is different. Remember, neutrons and protons have a mass that will account for, electrons do not. As you can see, the 24 by the right compared to the left, 23, tells us that it has one more neutron. Isotopes generally have very similar chemical behavior because chemical behavior depends mainly on the electrons, and neutral isotopes of the same element have the same number of electrons. The important distinction is that changing the number of neutrons does not change the element. Changing the number of protons would change the element. We use the mass number to keep track of the total number of protons and neutrons. Isotopes, we use this particular form. It can be represented by the element symbol, AZX form. The upper number is the mass number. It's equal to the total number of protons plus the total number of neutrons in the nucleus. The lower number is the atomic number, which is equal to the number of protons always. The element number identifies the element, so you put the element name there. And then we find that based off of the number of protons. And the number of neutrons, we just subtract the number on the bottom left, the Z from the A, and that tells me how many neutrons I have. This notation gives us all the information we need to identify an element and determine its protons, neutrons, and if it's neutral, the electrons for that particular isotope. So yes, I could also have plus or minus depending on what we were doing up here. Wow, that wasn't a great mark. Where most of that red circle is, I could have something like +2 or +3 or -1, and we'll talk about all of those in the next part. Concept check. Just kidding. Exercise. A certain isotope contains 23 protons and 28 neutrons. What? How will I know? Identify the element. First, we could probably figure out what the element is. You just have to go and look at a periodic table. Next, we would need to figure out how many protons that element has. Is 23. And then we're going to need to combine 23 and 28. That gives us, 51. And what is the element that is number 23? Vanadium. Therefore, this isotope in its mass we have, the process will always be the same. We use the protons to determine the identity of the element. We add protons and neutrons to obtain the mass number, and then we can subtract the atomic number from the mass if we needed to find neutrons. But in this case, it gave it to us. 3.4 will focus on using our periodic tables. First, we will learn the major features of our periodic table, including the order of the elements and the meaning of the rows and the columns. Second, we will compare the general properties of metals, nonmetals, and metalloids. Their location on the periodic table helps us predict how they behave. Third, we will examine the natural forms of several common elements. Some elements are found as individual atoms, while some of them are found in pairs or more called diatomic molecules. Some also larger structures. The periodic table is much more than a list of element names. It actually is organized very directly to help us recognize patterns and make predictions about the properties, ions, and chemical behaviors of those elements. Buckle up. The periodic table, that guy, contains the known elements arranged in order of increasing atomic number. So the atomic number and the number, which is the number of protons in the nucleus. So each step from 1 to 2 to 3 to 4 are one more proton. So as we go from left to right, we are increasing by 1. The table begins with hydrogen on the top left, and it continues across each row until it hits the end of the row and it moves down. 2 rows displayed below the main table are actually part of the same sequence. They're just underneath because it was the only way to keep the periodic table as compact as it is. So if you look where there's a star on number 57 and the number it has is 57, you just have to continue to count from 58 to 71 down there. The lanthanides and actinides we'll talk about much later, but because they are not as abundant as the top, let's say 50, we don't talk about them a lot in this class. The periodic table is arranged so that elements with similar properties are in the same vertical column. These columns are called groups or families, depending on what we're talking about. The diagram over here highlights several important groups. The first column contains the alkali metals, and the second contains the alkaline earth metals. Near the right side are the halogens, followed by the noble gases in the final column. The broad center region contains transition metals. Elements in the same group often form similar ions and react in similar ways because they have related outer electron arrangements. That's a lot right now. Just know that we'll talk about it later. But the horizontal rows, we call those periods, but the vertical columns are especially useful when predicting chemical behavior. As we move on to ions, these group patterns will help us predict the common charge. The periodic table can also be divided into metals, nonmetals, and metalloids. Most elements are metals and are located on the left side of the table, all the center of the table, and the nonmetals are concentrated on the top right side, along with hydrogen, the number 1 up on the left. Metalloids lie along the stair-step boundary between the two major regions. They have properties associated with metals and some with nonmetals. The location of an element gives us a useful first prediction, if we don't know anything about it, of its behavior. Metals commonly lose electrons and become positive, while nonmetals typically gain electrons and become negative ions. Metalloids often are a weird intermediate. The diagram is the map that'll connect an element's position to its broad classification. Physical properties of metals. Metals are efficient at conducting heat and electricity, which is why metals are used in cookware and wiring and electric components. Metals are malleable, which just means that they can be hammered or rolled into a sheet without breaking. They're also ductile, which means they can be pulled into wires. Many metals are lustrous or shiny in their appearance when the surface is cleaned. And these are the general trends rather than like a statement of every metal behavior. But the properties help distinguish metals from nonmetals. Later, the way metal atoms are arranged and share their outer electrons are a better explanation of why they conduct energy and can be reshaped without the entire structure breaking. But for right now, these 4 points are very important for you to know. The natural state of most elements are reactive, so they are not usually found in nature as pure uncombined elements. Instead, they occur as parts of compounds. This slide will list the important exceptions. Noble gases, including noble gases, the noble metals, including gold, platinum, silver, are relatively unreactive and can sometimes be found in their elemental form. And the noble gases in group 8 are also unreactive and occur as individual atoms. The term noble represents their limited tendency to combine with other elements under ordinary conditions. For most of the other elements, the elemental form must be obtained by chemically separating an element from a known compound. This is another reason that the materials around us contain so many compounds rather than just finding isolated elements. Did you know some elements exist naturally as diatomic molecules? The prefix di, as we'll learn, means two, so each molecule contains two atoms of the same element bonded together. The particle model that we have up here shows N2 nitrogen and O2 oxygen. Each blue pair represents two nitrogen atoms joined together, and each red pair represents two oxygen atoms joined together. Even though each particle contains two atoms, these substances are still elements because it's only that kind of atom that's represented. The diagram also shows the molecules are separated and moving through the container, which is consistent if they're gaseous, like these ones are. When these elements appear by themselves in a chemical equation, we must use their correct diatomic forms rather than writing single atom symbols. So we will be using N2 and O2 when we need to work with oxygen and nitrogen. Here's a list of the diatomic molecules. I use the friendly moniker Hibroclif. That's Hibroclf. And then I just remembered nitrogen, I guess. So you could say Hibroclifen. But regardless, these are the ones you'll need to remember and often are marked on the periodic table that they are diatomic in some way. Um, the physical states and the colors differ for all of these, but all 7 of them share the same structure of having two identical atoms bonded together. The subscript 2 is part of their formula for all the elemental substances, and it has to be included. So you see all these have their 2's. We'll have to make sure we remember those. An element can sometimes form more than one solid structure. As you can see up here, where's my Minecrafters at? The slide here, we're going to see 3 forms, all elemental forms of carbon: diamond, graphite, and Buckminster fullerene. Diamond has a rigid 3-dimensional network. As you all know, it's very hard, not quite as hard as netherite. Graphite contains layers of carbon atoms, and the dashed lines are showing you that they're separated through those layers. And Buckminster fullerene forms like a hollow cage of a molecule. Each material, since it only contains carbon, is still elemental. However, the carbon atoms are connected and arranged differently, which produces very different physical properties. This is important to remember that substances properties depend not only on what atom is present, but also how many of those are bonded and how it's organized. Different structures give the same element different forms. And finally, we're here with section 3.5. We're going to introduce the final component, and sometimes the hardest component, ions and ionic compounds. First, we're going to have to describe what an ion is and how that's different from the neutral parent atom by either gaining or losing electron. Or second, we will learn the naming rules for positive and negative ions. And third, we will use the periodic table to change the uh, charge of an ion of the main group elements. The last step is that we will describe how positive and negative ions combine to form chemically neutral compounds. The major idea there is that an ion formation changes the number of electrons, but we don't touch the protons or neutrons. Therefore, an atom remains the same element while gaining an electrical charge. The balance of positive and negative charges will then determine the formula for ionic, ions in there, compounds. But what is an ion? Atoms can form ions by gaining or losing electrons. Metals tend to lose one or more electrons to form positive ions called cations. Remember, cats are positive. And the diagram uses magnesium as an example. A neutral magnesium atom has 12 protons and 12 electrons, so its charge is 0. We call that balanced. When it loses 2 electrons, it still has 12 protons. We don't touch those. But now it only has 10 electrons. So there are more positive charges by 2 than negative charges, so it becomes Mg2+. Notice that the nucleus size didn't change at all, so it's still just a magnesium. The only the only thing that changed would be the electron number. The cations are generally named using the parent atom, so Mg2+ is called a magnesium ion. The superscript charge, high, shows the electrical net charge, not the number of atoms. Nonmetals tend to gain one or more electrons and form negative ions called anions. The diagram shows the neutral chlorine atom gaining one electron. The nucleus still has 17 protons, but the atom now has 18 electrons. Because it has one more negative electron than positive proton, the ion has a -1 net charge and is written as Cl-. Anions are named by using the root of the element followed by the suffix -ide or -ide. So a chlorine atom becomes a chloride ion. And even better, we can call it a chloride anion. As with cations, the forming of an anion does not change the element because we don't touch the protons. The change of the charge comes entirely from changing the electrons. Ions and periodic table trends. This is an important slide, I promise. The common ion formed by a main group element can often be predicted by its position on the periodic table. Group 1 metals tend to lose one electron and form 1+ ions. Group 2 metals tend to lose 2 electrons and form 2+ ions. If we jump all the way over to the nonmetal side on group 7, the elements tend to gain 1 electron and form 1- ions, while group 6 elements tend to gain 2 electrons and form 2- ions. These are patterns, so the periodic table can act as a guide rather than requiring every charge to be memorized. The transition metals are way more complicated because they can form cations with more than one possible charge. And yeah, we'll learn about those. This diagram places the common ion charges directly on the periodic table. Group 1 examples show lithium, sodium, potassium, rubidium, and cesium forming +1 ions. Group 2 examples are our +2 ions, so aluminum, gallium, indium are shown with a +3 ion. On the nonmetal side, jumping across, we have oxygen, sulfur, selenium, and tellurium forming 2 minus ions, while fluorine, chlorine, bromine, and iodine are forming 1 minus ions. The transition metal region, it's a hellscape, and it's labeled separately because transition metals can form cations of various charges. And not just from neighbor to neighbor, but they themselves can have a +2 charge, a +3 charge, a +5 charge. The noble gases are not assigned a common ion charge because they are generally unable to form ions. We call them inert or unreactive. Use the location and group patterns when we're working with these to predict the charges for a main group element. Please. All right, compounds that contain ions. Positive and negative ions combine to form ionic compounds. Ionic compounds commonly have high melting points because the oppositely charged ions attract one another, like a magnet, strongly. They can conduct electricity when melted or when dissolved in water. So if we think about something like, in this example, we have uh, salt that gets dissolved, and that will let electricity pass through, but pure water will not. That is because those separately charged particles allow the charge to move throughout the solution. The big idea here is that they have high melting points and they conduct electricity if melted, so high temperatures, or if they're dissolved. Ionic compounds are electrically neutral overall. This just means that the total positive charge from the cations has to exactly match the negative charge from the anions. The individual ions remain charged, but since it's a compound coming together, the net or the total charge is 0. When writing ionic formulas, we do not simply place each one of the ions together automatically. We must determine how many cations and anions need to make the charge sum 0. +1 ion and a -1 ion combine in a 1-to-1 ratio, but if we have a +2 ion and a -1 ion, then we would need a 1-to-2 ratio, and it changes from there. The balance controls the subscripts in those formulas. Formulas for ionic compounds. When we write our ionic compounds, the cation element always goes first, and the anion element always goes second. Then we choose the smallest whole numbers of each ion to make the total charge equal to 0. So if we look at this diagram, the diagram shows us the magnesium ion +2 charge and the chloride ions -1 charge. One magnesium 2 plus requires one magnesium 2 plus requires 2 chloride minus ions because the positive 2 plus and the -1 need to equal 0. The formula, therefore, is MgCl2. The subscript 2 applies to just the chlorine, and it tells us that chloride ions are present for every magnesium ion. We do not write charges in the final neutral formula. We do not write a subscript for the 1 in the magnesium because remember, we've got to be lazy somewhere. Exercise time. A pair of ions is listed below. What is the formula for the ionic compound it forms? Potassium and oxygen, K plus and oxygen 2 minus. So we need the smallest whole number combination to get those charges to be 0. If I have a +1 and a -2, how can I get the total charge to be 0? If I put 2 potassiums, that's right. So with my 2 potassiums and their positive charges balancing out the -2 charge from the oxygen would give us 0. So I need to follow my rules, and I know that I have to put my cation first, and cats are positive, so potassium must go first, and I need 2 of those. So I'm going to put a subscript 2, followed up by my oxygen. I don't really have to do anything special with that, other than we leave the 2 minus at home because they cancel out. That would give us K2O. We did it.